The purpose of this video is to help you learn how to use the Jet 10 aircraft modeling and analysis software by demonstrating how to use the software to optimize an aircraft for a particular design mission. The aircraft we'll be optimizing is the F-104 Starfighter. You can see it modeled here on the left side of the Jet graphical user interface. And in the center you see some analysis results for the aircraft geometry. The particular design mission that we'll be optimizing for in the design requirements are ones that come from the notional Air Combat Fighter Request for Proposals 1955 vintage. And this is what might have been a study about what if history had played out differently could have produced an effective air combat fighter for use during the Vietnam War. The requirements that are of interest to us in particular are the mission requirements here and the point performance requirements and other minimum performance requirements specified by the RFP. Now what we have modeled in Jet at the present time is the baseline F-104 defensive counter-air mission, essentially a point defense mission with a 150 nautical mile radius. And so we need to modify the mission and the design performance constraints in order to model the requirements for the ACF and then proceed to optimize the aircraft to meet those requirements. So let's just start right here with a service ceiling of 50,000 feet. Well, that doesn't change from the F-104. We've got that already in the constraints. How about the runway length of 8,000 feet? Once again, that's in there. The NATO standard runway is 8,000 feet. And so most aircraft designed to operate with our NATO partners need to be able to safely use a 8,000 foot runway. Now with single engine airplane, to safely use an 8,000 foot runway requires being able to accelerate to takeoff speed and then lose an engine and abort, come to a stop in the remaining runway. And that's what we've got modeled here. We've got 4,000 feet for takeoff and then 8,000 minus that 4,000 for the takeoff abort distance. It's labeled landing there, but it's really a takeoff abort. Next requirement, 6 missiles and the gun with 500 rounds. Now elsewhere in this RFP it says 4 AIM-9 missiles and 2 AIM-7s, and so that's what we need to model for our expendable payload. Right now for expendable payload we have just 2 AIM-9s and then the part of each bullet that fires. So let's go down and look and see what we have to do to model 6 missiles and the gun. Go down here to attachment 5 and notice that it lists the weights of all the various components we have to carry. You see down at the bottom the 20 millimeter ammunition. The cases weigh 0.26 pounds, but before they're fired the bullets weigh 0.58 pounds each. So the difference is 0.32 pounds. So the 0.32 will go into the expendable payload times the 500 rounds. The gun itself weighs 275 pounds and the drum that carries the ammunition weighs 300 pounds for a total of 575 pounds. So that will go in the permanent payload, the 0.26 times 500 and the 575. The other thing that goes in the permanent payload is the pilot's weight. Now the reason we show the gun as permanent payload is because on the F-104 the gun can be removed and a fuel cell placed in that gun bay. And so the gun is not really part of the empty weight, although it's often included in the empty weight when you see the empty weight published. So that's why our empty weight shows 1,300 and 255 pounds. If we included the gun in that and the ammunition, we'd get closer to the 14,000 pounds that's published. What else? We need to change our expendable payload to include 4 missiles now, 4 AIM-9s, and then also 2 times 514 pounds for the AIM-7s. And so that's our total expendable payload. Now there's also rails and launchers and things like that, but those are included in the armament category on the weight tab down here. We'll look at that thing later. Now one thing that happened when we entered this higher payload without changing the aircraft max takeoff weight is the only way to keep the same max takeoff weight is to reduce the fuel if you add more weapons, and that's what happened. So if we wanted to keep the same amount of fuel and still be able to fly this mission, we could increase the weight of the aircraft so that now we're carrying enough gas to fly the mission. There's problems though, because when you increase the weight of the airplane, it no longer makes the takeoff or the landing constraint and the turn constraint as specified. So we'll have to optimize this airplane in order to get it to meet all those requirements, and we'll probably have to resize it. But we've got our payload in there. Let's go back to our requirements table and see what else we need to do. It says a 300 nautical mile radius mission. Right now, let's just change this cell here to 300 so that we have a 300 mile radius mission. There's more details of the mission that we'll include later as we look at the mission, the specified design mission page. But for now, let's just make it a 300 mile radius mission so that the total mission range over here is 600 nautical miles. And let's proceed putting in the other requirements. One of the requirements is 5 Gs at 20,000 feet and 0.9 Mach. So we'll put that in there, 20,000 feet, 0.9 Mach, 5 Gs. And then 3 Gs at 20,000 feet and 1.2 Mach. We'll put that one in there too. Notice as we make each change, this constraint diagram updates. The next requirement is a maximum level flight Mach of Mach 2. So we'll put that in there for max Mach, 36,000 feet. It's already in there. And it doesn't really say it, but of course we have to be able to cruise at the design cruise Mach at something like 36,000 feet. We pick our cruise Mach equal to our aircraft's critical Mach number, and so that right now is 0.88. So those are all those requirements to that point. Now we do 2 minutes to accelerate from 0.9 Mach to Mach 1.5 at 36,000 feet. These last 3 constraints are all the same. You don't want to delete constraints because it'll mess up the way JET automatically chooses an optimum design point. So we just duplicate them. We just duplicate the last 3. So 36,000 feet. Let's go over here and calculate what rate of acceleration in P sub s this is. So 2 minutes to go from 0.9 Mach to Mach 1.5 in 120 seconds. So that's a dVdt of just under 5 feet per second squared. And that, using the equation for P sub s, comes out to 145.8 P sub s. And so at 36,000 feet we have to be able to achieve that, to do that acceleration. So we've got that entered in. Now all of our constraints are entered, and we're ready to look at the last 2 requirements on the table. And these are based on cost. The non-recurring engineering costs are supposed to be less than $1 billion, and the unit cost less than $10 million each for a 2,000 aircraft buy. So first off, let's change to 2,000 aircraft. Boy, those were the days, 1955, and costs were really low back then too. We say 21 million, $4 billion, for NRE. Well, that can't be right, but of course not. Our cost model is set up for a different year. Let's look down here. The costs are calculated for 1999 and escalated to 2006. We want to change that to 1955. And we do that not just by typing in the date, but we also have to change the escalation factor. Now, going from 1999 to 2006 is the escalation, or the inflation over those years, is 116%. So the escalation factor is 0.16. In other words, it's 116% minus 1. When we go back to 1955, I'll let you look that up yourself, but I've done it. I've looked it up, and I find that $100 in 1999 would be worth $16 in 1955. So what that means is we do 0.16 minus 1 to get our escalation factor for 1955. It's just a coincidence that the factor is 0.16 again. It was 116%, and then it's 16% going back to 1955. So when we do that, we get an escalation factor of 0.84. We get a NRE of about $600 million and an average unit cost of about $3 million. So that's good. That's well below the limits. So we can hopefully, even when we resize the aircraft to meet all the requirements, we'll still be okay. Let's go back to the main page. We're almost ready to optimize now. We still have to model the design mission, which is the first one. The primary design mission is an offensive counter-air mission, and this is what it looks like. Fuel allowance for takeoff, warm-up and takeoff, that's what this STTO models, and that number will change as the engine size changes. We take off and climb. That's modeled again in this first leg. The takeoff is. Then we climb from sea level to cruise altitude. Well, we have to accelerate to climb speed of 0.88 Mach, so that takes a little bit of distance, and we're doing that at just 500 feet above the ground. And then we'll start our climb. That may be a more efficient way to do it. Climb from sea level to our optimum cruise altitude. Now, the optimum cruise altitude is calculated by jet, the best cruise altitude, but that's usually if you didn't have to pay gas to get to the altitude. That's really what it's based on. It's based on the altitude where your mcrit is also your Mach number for L over D max. And that's the highest altitude you want to go to for optimum cruise range. But because it takes gas to climb up there, we usually stop short of that altitude to get the least fuel burn. We'll experiment with that once we get our aircraft closer to being optimized. It says go out 250 miles total, including previous legs, for the mission cruise portion, and then dash 50 nautical miles above 36,000 feet. So the way we've got it modeled is adequate for the time being. Then it says perform 4 360-degree turns at 0.8 Mach and 10,000 feet. You can do it above 10,000 feet, but that's probably one of those things where we could leave it at 20,000 feet. Why don't we do that and see how long that's going to take us at 20,000 feet. 4 turns times 360, so we put a formula in there, equals 4 times 360. And 20,000 feet, 5 G's and 0.9 Mach, or 0.88 Mach. It says 0.85 at least, so it'll take less time if we go at 0.85 Mach. Okay, and we know we can do that because we've got a constraint that says we have to be able to do that. So that's fair, and that takes us about 2.5 minutes. So let's put 2.5 for our combat time in the mission analysis at 20,000 feet. And then we're going to deliver all of our expendable payload. Then we're going to egress at Mach 1.4, climbing to 36,000 feet. And these altitudes are end altitudes. You see if over here it says end altitude in feet. So if we end up at 36,000 feet at the end of our egress, we've done the required mission leg. Then descend to best, or climb to best cruise altitude. We're guessing this patrol leg is nothing, it's no time, and so it just doesn't do anything. But don't delete it because it'll mess up how JET calculates the total mission fuel burn. Then we climb to 40,000 feet, so we're going Mach 1.4. We just zoom up probably to 40,000 feet. Probably 0.88 Mach is our best cruise Mach, so let's make that 0.88. Here, let's make this 0.88. Okay, and that'll get us back home. Descend to sea level. Now there's one more leg that the airplane doesn't actually fly. It's a loiter leg that's designed to calculate fuel reserves. And this loiter leg is a way to figure out how much gas you need in case the runway has been bombed or it's got lots of bad weather around it and you have to wait a while, or you have to divert to another base. That's a standard fuel reserve calculation for a fighter type aircraft like this. So there we have it. We've got our design mission, we've got our design constraints. I think we're ready to optimize this airplane. Well, for starters, it doesn't make the landing constraint. It does just barely make the takeoff constraint, but it doesn't make many of the other constraints. And honestly, I think we've already we haven't really done anything yet to the aircraft. We could try increasing the engine thrust to the thrust available from a newer version of the J79. The J79 modeled is the one in the F104C, and you can see its maximum thrust is 15,600 pounds. There's a new version, the Dash 15, that we could put in here and it'd fit in the same space, 17,000 pounds of thrust. So let's put that in there and see if that helps our situation at all. And you know, it really doesn't that much. I think we just need significantly more thrust for this aircraft. So let's bite the bullet and put in the bigger engine. This is a J75, it's a heavier engine. But it's got significantly more thrust, 24,500 pounds of thrust and 16,100 pounds in mil, especially better in mil. We could also just go to 2 engines for the F104, but that's probably more thrust than we probably want to pay for. Hate to have to pay for 2 engines. So here we're looking a lot better. We could actually meet all the constraints at this point, except we wouldn't carry enough gas. We could shorten our takeoff distance to say 3,500 feet. And now we meet all the constraints except for the turn constraint. We could fix that by making the wing bigger. Notice on the constraint diagram that when the plus is over to the right of the circle, that means your wing's too small. Let's try 300. Alright, that's lots better. Our aircraft meets all the constraints, and the only problem is we don't carry near enough gas. Airplane's not near heavy enough. We need to add 5,000 pounds. Let's go to 30,000 pounds. And even then it wasn't quite enough. Okay, 31,000. Getting close, 32,000 pounds. Alright, so now we have enough gas. We're meeting all the constraints except for the turn constraint, and we have a problem with volume. But part of the problem is just the fact that the engine got bigger, and we haven't allowed for a growth in the fuselage to accommodate that extra size engine. In fact, the engine's sticking out several feet behind the end of the airplane. So let's start by lengthening the aircraft to enclose the whole engine, and then let's look at the A versus X plot and see where we might add some cross-sectional area without harming the aircraft's wave drag. So it looks like after the max thickness point, about 36, 37 feet, we can start adding both width and height. And I'm just going to link the width and height, keep the fuselage round here, and I'm just going to copy this down so that when I change one, it'll change the other. And that'll just save some time. Alright, so let's go 5.5 here. Okay. Looks like maybe we could go 5.2 or something like that, even further forward. Let's try 5.5 here. And let's try 5.5 there. Okay, and maybe 6. That's starting to look a little better. Let's try 6 here. Nope, let's keep that 5.5. Let's try 5.2 here. We're trying to make a nice smooth shape back there. Okay, that looks pretty good. And then we're coming on down to 4.5. Well, let's do 5 and 4.5 and 4. Didn't use my copy situation very well. Let's put 5 here. That's better. The rest of that looks pretty good. 4.5. Let's try 4.2 and 4. Alright, that looks better. Now, the engine is 43 inches in diameter, so we can't go much less than 4 feet in diameter, or we won't have room for structure around the engine. So that's kind of what it looks like back there, to enclose the engine in a reasonable way and give us quite a bit of extra volume in the process. Look at this. We've got, we only need 6 more cubic feet of volume and the airplane's done, except we're still not making the turn requirement. Okay, so let's try changing the wing shape in order to help the turn requirement. Let's try to go to a 3 aspect ratio. Wow, that had a huge effect. Not all good. We don't have enough gas now because the higher aspect ratio, the wing weighs more. And we're not doing well with all these high Mach number requirements. So, and also the high G requirements. So there's a couple things we can do. First off, let's try to save some weight on the wing. Right now the wing has a 3% thick airfoil. That's what the 104 had, but most 4th generation fighters have a 4% thick airfoil, so let's go with that. 4% thick. And that saved a lot of weight, but it also made us burn more gas, because in the high Mach number regime we have a lot more drag. We're burning a lot of gas there. It's our most, aside from combat, it's our most fuel consuming leg. So let's sweep the wing more to help it go faster. Let's go to 30 degrees of sweep. Oh, that cut everything. That cut the fuel burn quite a bit. Let's go 40 degrees of sweep. That cut the fuel burn even more. We're just 1,000 pounds light on fuel, and we're almost making the turn constraint. Now there's something else we can do to change, to save weight on the weight of the wing. And of course, when the wing weighs more, the airframe weighs more, and we carry less gas for the same takeoff gross weight. So we need to try to make that wing weigh less so that we can carry enough gas to fly the mission. The F-104 had a 0.38 taper ratio. If we can go down as low as 0.23 for this wing and feel confident that it'll work, the F-16 has a 0.23 taper ratio. So let's put that in there and see if that doesn't help us. Oh yes, it did. It saved some weight of the wing, a couple 100 pounds, and it actually sort of helped us fly that combat turn a little bit better too. Now the only way to really fix that combat turn is to make the wing bigger, I think. You can see on the constraint diagram that the plus is over to the right of the circle, and that tells us that our wing is too small. Let's try 350. Okay, now the plus is in the circle. We're 1,000 pounds light. Maybe we can help some of that by changing the aspect ratio again. Let's try 3.5. Burned less gas, but it added a lot more weight. I'm not sure that's going to be the right answer for us. Let's see what else we can think of doing. Let's go back to the aspect ratio 3. And let's think about changing our cruise altitude. Bigger wing, our altitude for M-crit equal the Mach for L over D max is going to be higher, so let's climb on up. Let's see if 39,000 feet is worth doing. Saved a little bit of gas. Let's try 38,000. That saved more. And then coming back, it looks like we can go higher, maybe 44,000. I'm thinking maybe 42,000. No, that was more, 43,000. Okay, that's about as low as it gets. So, the good news is we're making all the constraints now, and we probably just need to increase the weight of the airplane. So let's try 34,000 pounds. And the only thing we need is a little space. We've got a pretty good design here. We could use a little more wing area to get the extra space. Let's try 400. We can put fuel in the wings. And there we are again. Now we're just a couple hundred pounds. Let's try 34,400. And 400 pounds of gas take up 8 cubic feet, and that's exactly where we are. We can go 34,300 and only need 6 cubic feet. And then I think we can probably gain those cubic feet in the forward part of the airplane, up here ahead of the AMAX. So you can see there's kind of a little saddle here. We'd actually like to beef that up a little bit. So let's start broadening the aircraft just after 20 feet, 21.6. Let's go wider, 5.5. That helped a little bit. Let's go 6. And we've got our volume. Maybe we'll go back to 5 there. Maybe we'll leave that alone. Alright. And then the other thing we might do is try to area rule this airplane just a little bit. Here where AMAX occurs at 37 feet or so. Let's try narrowing it down just a little bit. Let's try 5 there. That cut it down. Let's try 5 on the next one. And even 4.5 on that first one. So just a little bit of 4.5 on the next one. A little bit of area ruling. Cuts down the fuel burn. It does hurt our volume problem, but we can drop our weight. 34,200. Okay, and we still need some cubic feet here, so we'll add those cubic feet in ahead. Let's go 5.3 for width. And I have an idea. You see how the F-104's fuselage at the rear of the cockpit there at about 17 feet. Next back down, I'm thinking we're going to keep that longer, but there's a fuel tank right there. We're just going to make it a bigger fuel tank. So it's right at about 16.2 feet. It's 6 feet high. Let's just keep it 6 feet high for a little while, and I'll bet we get our volume back pretty fast. That was not all what I wanted to do there. Yeah, let's try 5.5. There we go. So we got plenty of volume now. The airplane closes. It looks a little silly because the horizontal tail's too small and the vertical tail's too small. So let's try to clean that up. First, let's give it flaperons instead of flaps and ailerons. That way we can put the actuators inside the fuselage and we don't have to put any actuators in the wings. F-104 had some crazy aileron actuators inside the wings, and we don't want to do that if we don't have to. This will keep the airplane simpler, easier to maintain, and more reliable. So the way we do that is we take our ailerons, and for each, we're doing an autosave. For each entry for the aileron, we have to make it equal to the entry for the trailing edge flaps, and then it'll become flaperons just like the F-16 uses. So here's an area, here's an aspect ratio, here's a taper ratio, which is the same, here's a sweep, which is also the same, here's an airfoil section, which we can't use the copy function there because of the formatting of that particular cell. And we'll make this one equal to the X location, we'll make the Y location equal, doing that on the strakes instead of equal here, and we'll make the Z location equal, and we'll make the dihedral equal. Alright, so now we've got flaperons. Let's give them a little higher aspect ratio. Let's go about 6, and let's make them bigger. Let's go about 45. We've got a big wing there. This says that our leading edge flaps need to be big because we have a supersonic leading edge at the maximum Mach number. So our leading edge needs to be sharp, so we have to have leading edge flaps. And that's okay, we can do that. They need to be at least half as big as the flaps on the wings. Maybe we'll even go higher aspect ratio 7. That'll give us a little more roll control. That looks pretty decent. Not that different from an F-16 wing. Alright, let's go to fix the vertical tail. Well, first off, the vertical tail can go further back, and that's going to help. And then the vertical tail can get bigger, and that solves the problem. Alright, and then our horizontal tail looks silly. It's very tiny. Let's go to maybe 100 on the horizontal tail for an area. And not only that, let's move it down. The F-104 and the F-101 both had T-tails like this, and it didn't actually work out very well. At high angles of attack, the T-tail would get blanked out by the wake of the wing. The aircraft would pitch up and go out of control. So we don't really want that kind of behavior. So what the F-100 and the F-4 and T-38, various F-5, F-16 do is put the horizontal tail down low. So let's move it down low. Right now its Z coordinate for the pitch control surface is 8 feet. Let's make it 0. Puts it down kind of right behind the wing, but I'm not sure that wing needs all that anhedral anymore. Let's get rid of that. Let's go to 0 dihedral. That might help our CN beta. The wing was probably destabilizing a little bit. And then we can actually move the horizontal tail forward a little bit so it's got a good hold of the rear fuselage. And it's a good size. And the only other thing we might do is give it some anhedral, maybe 5 degrees or so, to get it out of the wake of the wing. That's what they do on the F-16 and on the T-38. Let's try -10. And that looks pretty good from the front. It looks like that's in clean air down there. It's not going to get in the wake of the wing. We gained a little weight when we added the vertical tail, and the vertical tail is probably just a little bit too far back. Let's try 43. I was afraid of that. Let's try increasing its aspect ratio. That makes it a more effective lifting surface. When it had that horizontal tail on top of it, a lower aspect ratio tail was a good idea, because you've got all those loads out there. You don't want to have a heavy structure to hold a long, slender vertical tail. But now that the horizontal tail is firmly mounted on the fuselage, we can have a higher aspect ratio horizontal tail. And that's to our benefit. We can actually reduce maybe to 75 square feet, 76 square feet. Okay, we've got enough CN beta, we've got a good ratio of CN beta to CL beta. I think this is going to be a pretty nice flying airplane. We're just a little light. Let's go 35,000 so that we're still a couple hundred pounds short. Let's go 35.5. As the airplane gets heavier, then it burns more gas, so that's a problem. And it looks like we meet all our constraints. You could argue over on the constraint diagram that we should have a bigger wing. And for the next step, which is wing optimization, let's go ahead and make that wing bigger. Just a little bit bigger. Let's go 450 on the wing. And that puts, let's go 440, I guess. That puts the dot in the hole. And let's go 36,000 on the weight. And we're right there. Okay, so we've got an aircraft that closes. Now that we say the wing is just a little too big. So 430. Let's try 420. And now we've got a reasonable design point, which is centered right below the center of the optimum design point. The optimum design point is chosen to give some margin over the constraints, and that's maybe because we're below the center of that, we're probably being a little risky in terms of not allowing some margin over the absolute limits of our design space. Notice the vertical tail again is too small, but let's fix the center of gravity first. We made the airplane longer. I'm sure the center of gravity is going to move, and it did. We see here that with no stores or fuel, center of gravity is at 35.2. So if we can kind of choose where the stores are carried by the way we design our pylons. Let's make it 35.3. And the idea here is we put the stores in such a way that the CG doesn't move when we fire our weapons. And we also put the fuel evenly distributed in front of and behind and on the CG. We can do that by the way we design our fuel tanks. The idea there is minimum CG travel. But what that did to us is reduced our static margin and reduced our moment arm for our vertical tail. Let's try that trick of increasing the tail's aspect ratio again. It doesn't look too bad the way it is. Increase it, we're almost there. It's a pretty nice looking tail. Let's try 1.6. Almost there, 1.65. That's a pretty nice looking tail. Hey, we don't have any red boxes anymore. I think this airplane is just about ready to go into production. Static margin is low. That would mean either move the wing back or sweep the wing some more. And I prefer adding a little bit of sweep. I don't want that wing running into the horizontal tail. So let's try that. A little bit of sweep. Let's try 43 degrees of sweep. It's also reducing the fuel burn when we do that. So let's go 35.7. And that's really, really close now. Well, that's a nice looking airplane. One of the things, looks like we need just a little bit more 77 on the vertical tail. 35737 for the takeoff gross weight. Airplane closes. All right. Now we have a good solution to the sizing equation. It's very close to our actual solution that we've got. We've got our plus very close to the circle. So we can do sizing and optimization. So what we're going to do, we have an aspect ratio of 3, we have a sweep of 43, and a taper ratio of 0.23. And one other thing we might do before we do the optimization is try a little camber. Let's see if that helps us at all. 1404. You don't want to, oh yeah, that did. Oh, look at that. We can drop 300 pounds or so. Let's try 35437. Let's 5. Yeah, great. So that camber helped us just a little bit. You don't want to go overboard on camber because in a supersonic airplane, camber penalizes you at the high Mach numbers. But 1% camber, that's what the F-16 and F-15 use, and in their baseline airfoil, so that should be okay. Now I think we're ready to go optimize. Notice again the solution to the sizing equation here is and the wing area is very close to our actual. So if we do some variations around that, we should get reasonable results. So we're at aspect ratio 3, so let's go from 2.66 to, or let's go 2.8 to, let's say 4 in steps of 0.2. Let's go sweep angle, we're at 43 degrees, so let's go from 30 degrees to 50 degrees in steps of 2, and taper ratio is 0.23, and thickness to chords 4% and 1% camber. So we have to be very careful as we set the limits to these iterations, because you can create an infinite loop if you don't have limits that are ever going to be achieved. And so you may want to save your work at this point before you do the optimization, because you may find that if you did something wrong and get an infinite loop, you have to X out of the whole thing and start over. So let's hit the calculate button. It's going to try every aspect ratio and sweep angle in the range. There we go. Looks like we're getting all positive solutions. That's good. So we should have a nice tightly grouped little, oh, that's a beautiful carpet plot. And it looks like the optimum aspect ratio is 3.4. And the, let's look at the optimum sweep angle. So we're looking for the lowest fuel burn. Looks like it's 97.41 right there. And it's a sweep of 42 degrees and an aspect ratio of 3.4. So let's give that a try. 42 degrees, 3.4. 3.4, 42 degrees. Well, this doesn't look real promising except for the fact that now it looks like the wing's too big. And it looks like if we make the wing smaller, we can do a better job of meeting the constraints. And so we're getting closer. Let's try 380. And that's probably where we're at. It turns out the particular wing that came from optimization wasn't that much better. It looks like it's actually worse from the point of view of size, takeoff, gross weight that allows the aircraft to close. But sometimes that optimization genuinely gives us a better design. Let's Control Z and Control Z again, and oh, it's in another save, sorry. As soon as the save is over, we'll Control Z and Control Z again, go back to our other aspect ratio. .43 and Control Z one more time. So it was burning a little bit more gas, but we could carry the gas. So you're going to have to try to make a decision here about, well, if I'm going to operate this airplane for 30 years and I save a couple hundred pounds of gas each mission, and I have 2,000 airplanes, that's a lot of money. And if the price of the airplanes isn't really that much different, we may want to go with the other wing that was recommended by optimization. We said that was 3.4, and 42 degrees of sweep. Saves 100 pounds of gas or something like that, but maybe when we make the airplane heavier, it won't really. Yeah, see, I don't think it's actually helping us that much. Let's Control Z out of that again. Control Z once, Control Z twice, Control Z 3 times. Okay. And this airplane looks good. Essentially, optimization proved to us that we had a good optimum design by hand. The automated optimization just proved that that was correct. One last look down here as we've moved our wing around. We've got a decent static margin. I don't want to mess with that. But our wing ended up a little further back, and so we have an issue with the A versus X. It's got kind of a peak right there, right at 40. And so we just want to make that 5.5 or something. Take the edge off of that, maybe even 5. And what do you know? We saved a couple 100 pounds of gas. 35,300. All right, I think we're about ready to say we're done with this process. It's just a couple of quick things we need to check. We need to make sure the landing gear are correct. So let's go to the gear page. We made the airplane longer, so guaranteed the gear are not in the right place. Notice the fuselage looks a little lumpy here, and we can smooth that out with some changes to the vertical location of the center lines of the fuselage cross sections. But let's fix the gear first. Okay, so the gear needs to be back further behind the CG. We want a 90-10 rule, so let's go. Well, we have 16 degrees right there. If we make the gear taller, we maybe get the tip back angle correct. So 5.5. Right now we're not able to rotate. Okay, let's try a little further back, 36 or 37.5. And we've got a good, we can go, yeah, that's too far. That's 19 degrees. Let's go 37.2. 16, 17 degrees. Yeah, let's stick to 37. That's right at 15 degrees. We'll just make the gear a little bit taller, 5, or let's make it 6. And that, let's, now we do have to go back again here, 37.3 or something. Alright, that's good. 90-10 rule, we can fix that by bringing the nose gear back. That's a very nice 90-10 rule. But the problem is we can't rotate for takeoff because our pitch control surface is too small. So let's make it bigger. It should be about almost half the size of the main wing. Let's try 150 square feet. Let's see what that did for our takeoff rotation. And we're getting there. The CG's moving a little bit, so that's an issue too. Let's try 200. And I'll bet we can rotate for takeoff now. Yep. And our CG moved back a little bit. We can move our gear back, 37.5, 38. And we're good. We've got a 90-10 rule, a little bit on the 87-12 side of 90-10. That's good. We can rotate for takeoff. We've got a big enough horizontal tail. We probably have the horizontal tail stuck too far back. Looks kind of large there. And it weighs kind of a lot, so we have to increase the weight of the airplane. Let's go back to our 36,000 pounds. And let's, just to be safe, 37,000, we're going to call it good. And there's other ways to do that, but okay, 36.7, 36.7. But the point is, we're making all our constraints we're a little worried about this turn constraint at 20,000 feet and 0.9 Mach. So let's check the maneuverability diagram for 20,000 feet just to make sure. 20,000 feet, 0.9 Mach, 2, 3, 4, 5. Yeah, we make the 5G requirement. So the airplane works. And maybe it looks funny, maybe the horizontal tail is bigger than we necessarily like. We certainly have to cut out part of it for the engine. Maybe there's more things we could do, but this is the basic process of optimizing an airplane for a particular design mission.